slope fields. The basic idea of slope fields is that this will give us a picture of the general solution to an antiderivative. Okay? It's the idea that we have a plus c on all of our antiderivatives, so the function could be shifted in a whole bunch of different places. Right? That's the idea here. And if in all the examples we've done so far with antiderivatives, we've only looked at one variable, right? We've looked at anti-differentiating a function in terms of x. Slope fields allow us to see a picture of a graph when we throw in x's and y's. Okay? Functions that we may have difficulty with finding the antiderivative by hand, we can at least see a picture of the graph using a slope field. Okay? Now, with this, we will actually get into finding antiderivatives of functions that have both x's and y's in them. Right? But to start, we're just going to use slope fields to get pictures of these graphs. Right? So let's take a look at this first example here. Okay, it just says sketch the slope field for dy dx equals 3x minus 2. So we're saying, here's our derivative. Use this derivative to sketch the general solution. So we're sketching the antiderivative when we're doing this. Okay, so this derivative is only in terms of x. Okay, so I'm just going to plug in some x values. And on this graph, we're just going from -2 to 2. So if I plug in these x values, if I plug -2 into my dy dx, 3 times -2 minus 2 is -8. Right? If I plug -1 in, I would get -5. If I plug 0 in, -2. If I plug 1 in, I would get 1. 2 in, I would get 4. So to sketch this, what we're going to say is these are our slopes. I'm going to go to x equals -2. So that's actually at all 5 of these points, right? Where x is -2. And I'm going to sketch a little line that has a slope of approximately -8. Okay, now that's a really, really steep negative slope, right? So it's almost going to be a vertical line, okay? But so I'm just going to kind of sketch a small line there with a super steep negative slope. I'm going to do the same thing all the way across, right? So at -1, at x equals -1, I'm going to sketch lines that have a slope of about -5. So that's still pretty steep, but maybe a little bit less steep. This is not an exact science.
It's not science.
Then at 0, I've got a slope of -2. That one's a little bit easier to maybe sketch out. And so something like this. Then at 1, we've got a slope of 1. So that would look something like that. And then at 2, slope of 4, so that's going to be a fairly steep positive slope.
Could these be like curved lines or like straight-ish lines?
So when we're sketching these little line segments, we're just making them straight. Okay, we're saying this is the slope at that point. We're just kind of making a little straight line there. Okay, so what we've just done is sketched a whole bunch of antiderivatives for this. Right? Now, this is a linear function. Okay, hopefully we can recognize that its antiderivative would be a quadratic. Right? So what we've sketched is a whole bunch of quadratics. If we kind of follow the path here, we can see that these are just going to create a bunch of quadratics, depending on where I decide to sketch it. Now, we are going to look at examples, and on the AP test, I don't know how they grade these questions, okay? But on the AP test, sometimes they will ask you, here's a slope field, sketch a solution curve through a certain point. Okay? So we'll look at some examples of that here in a second. We're not going to do that yet. But what we are going to do is solve this differential equation. This is where we're finally going to get into the importance of the dy and the dx part. So if I've got a differential equation like this, what I need to do is separate my variables. Okay, now something like this, we could easily take this, we could say, y prime equals this, take the antiderivative of 3x minus 2, and we'd be good. But this is a good introductory example to separating variables. I want to get my x's and dx's on one side of the equation, and my y's and dy's on the other side. Now here, all I would need to do that is multiply both sides by dx. Okay, so dx's would cancel here, and I just get dy equals 3x minus 2 dx. Right? Once I've separated the variables like this, now I take the antiderivative of both sides of the equation. Well, the antiderivative of dy would just be y. Right? So we'll get y equals, and then over here, we would take the antiderivative just like we normally would. So the antiderivative of 3x would be 3 has x squared minus 2x plus c.
That isn't c negative 2.
Why is c
Never mind. Wrong thing.
Okay. All right. So yeah, so this slope field shows all of these solutions. Okay. I mean, obviously, in this small little box, we don't see all of them. There would be an infinite number of solutions. But what a slope field does is sketches out a bunch of these possible solutions, okay, including this plus c idea. So what we would end up with is a quadratic over here somewhere, right? But that plus c could shift it up or down a whole bunch of different ways. That's the basic idea here. Questions? All right, so let's look at an example where we throw in x's and y's then. So here we've got 2x minus y times dy dx equals 0. So to sketch our slope field, we first need to just solve for the derivative. We need to solve this for dy dx.
Well, subtract 2x.
Subtract the 2x over. Divided by negative y. Right, so we get that our derivative is 2x over y. Right? So now, this isn't going to be as easy as plug in x equals negative 2 and it's going to be the same slope everywhere. It's going to change now since my derivative is in terms of both x and y. So let's just start picking some points here and see what happens.
Negative 2.
Right, let's plug in negative 2, negative 2. What do we get?
2.
4 divided by negative 2. So the slope of 2. So we can sketch that in here. And so here at negative 2, the slope would be 2. So something like that.
I said negative 2, negative 2. You said negative 2 up. You went over 2 up 2. I went down 2.
Oh, yeah, I did, didn't I? Oops. There we go. All right, so you guys go ahead and pick a few more points here and determine dy dx. sketch your slope on the slope field here.
Yeah, how do they grade this? Because my line looks almost exactly the same.
I think when they ask you to sketch a slope field, I think they're more looking for positive, 0, and negative. They're not looking for you to differentiate between a slope of 4 and a slope of 5. They're just making sure that these ones are positive, these ones are negative, and these ones are 0. I guess what I want you guys to eventually recognize as you're starting to go through them is there are a couple of patterns. So we will use all of the blocks, but on a few of them we can recognize some patterns. Did we get something that kind of looked like this? So hopefully we recognized a couple of things. One, if we plug in 0 for x, we would get a slope of 0, which means we would have a horizontal line. If we plug in 0 for y, we would get an undefined slope. An undefined slope is a completely vertical slope. Right? So here, at these values, we can have a completely vertical line. Now at 0, 0, though, we would have something indeterminate. We would get 0 over 0. So there would not be any slope there. Okay? We okay with that one? Now, the next thing that we want to look at is solving this differential equation. Okay? Just like we did in the first example, we want to separate the variables. There's a little bit more to it now because we have a y. So what I'm going to end up doing here, I'm going to multiply this y over, and I'm going to multiply the dx over. So what we would end up with is y dy equals 2x dx. Because now we can take the antiderivative of both sides.
What's the antiderivative of y?
So we treat it just like an x.
Okay.
So what's the antiderivative of x? That's the derivative. So the antiderivative
It's 1/2 x.
yeah, so this will be 1/2 y squared. Then the antiderivative of 2x,
Is
x squared,
plus
Let's see.
So we don't have plus c.
we only put the plus c on one side. Technically, it doesn't matter which side we put it on, but it's convention to put it with the x.
It has to be on a side.
Right. So now we would want to solve this for y. So, yeah, multiply both sides by 2. Okay. So, y squared equals 2 times x squared plus c.
Square root.
It's like the square root. So, forget the plus or minus, right? So we would get y equals plus or minus the square root of 2 times x squared plus c. So this slope field gives us a picture of what this could look like.
That looks like a very janky
I think this would be a hyperbola. Right? I think if we tried to sketch solution curves, it would end up looking like this and like that.
Oh, that would make sense. This is like looking at like abstract art, trying to make sense of it.
Alright. We okay so far?
Are you shutting?
Yeah, we should have time to go through this whole next example here.
I'm tired.
Actually, nah, we're going to skip to the matching part because we kind of talked about a lot of those ideas in that little mini activity there.
Yeah, I like matching.
Alright.
Oh, I found what number 8 is already. No, wait. This side one. Never mind.
Alright, I'm not going to be able to get a good picture of all these on there. Alright, so let's take a look at matching. Okay, we're given 8 differential equations, and 8 slope fields. We need to figure out which one matches up with which. One of the more common ways that this shows up on the AP test is they will give you a slope field and give you 4 options and say which of these is the correct differential equation that goes with this slope field. Okay, so matching is a good way to practice that. So what strategies do you think we might use to try to figure out what slope field matches with which differential equation?
Well, we know how sine and cosine kind of works. Like they're both really curvy.
Right. Yeah, I mean that's definitely gonna play into this. So yeah, we know what a lot of these parent functions, especially trig functions, would look like. So I mean, if we think about number 4, right, and we know that dy dx is cosine, we can actually easily figure out what y is. What would y be here? Sine, yeah. So for this, we would just be looking for which graph is sine of x, right? Or I guess, let's see, right? So we could be shifting that sign up or down.
Kind of looks like H.
Kind of looks like H. Yeah, I think that's probably the only one that actually looks like a trig function, right? So one strategy would just be to think about the actual antiderivative and what that antiderivative would look like. More often than not, though, we won't be able to use that strategy. Okay, more often than not, we'll have x's and y's, or even some ugly function, right, that we can't just think about, well, the antiderivative would look like this. So what are some other strategies that we could use? Yeah, where slopes are going to be positive or negative. Right, so number 7, for example, I've got negative x times y. On this one, well, if I plug in, if both x and y are positive, the slope's going to have to be negative, right? So here, I would be thinking, well, the whole first quadrant should have negative slopes. Right? So, yeah, it looks like the only option where that fits is B. Any other strategies that we could think of that might be useful?
Well, I'm pretty sure number 5, you can't have anything negative.
Right. So if we think about some of these graphs have blank spots, right? Well, that means there's either a domain or a range restriction. But here, we couldn't have any negative y's, right? That's definitely a good thing to recognize because we can't plug any negatives into a log. So that means this one would have to be E, right?
And then I think the other one that doesn't mean range might be 2.
Y might be.
No.
Well, remember this is the derivative. So we're thinking about pictures of the antiderivative. So one other thing we could use, if our derivative is just in terms of one variable, like in number 1 here, it's just in terms of x. In number 6, it's just in terms of y. Whenever that's the case, okay, let's look at number 1 first, for example. If it's just in terms of x, every slope at a single x value will be the same. Right? So if we think about plugging in where x is 0, well, at x equals 0, the slope is going to be the square root of 2 at every single point. Right? So we want to find a graph where the slope is exactly the same at every single point on the axis. Right? It looks like it changes here.
H?
Changes here. A, it looks like it's 0 everywhere. H, it looks like it's the same everywhere.
What we would use it.
But we did already use H.
Yeah. So.
D, it looks like it's the same everywhere. Right?
Wait, and there's a domain error in that one.
So, if we think about number 1, okay, we can't take the square root of a negative number. Right? So anything that we would plug in here that's less than -2 would make this not work. So if we combine both of those ideas, right, nothing to the left of -2 and the slope at the x values the same. Right? If we just look all the way down, the slopes are exactly the same. Right? So this one I think would be D. So using that same idea for number 6, since we said number 6 was only in terms of y, and our dy dx is y squared plus 1, in this case, we're looking for where the slopes are the same for every y value. So if I look horizontally, the slope would be the same all the way across. Right? So, yeah, it looks like C would fit that. Are there any others?
Yep, all of them are type first.
Yeah.
And these are really funky ones. F and G is really funky.
Yeah, because it's
What is it?
sine.
Well, I think A is more.
No, A is a 2. Because it's only in terms
Yeah, so this one, there's no y's, it's just in terms of x. So if I look at going straight down, right, at an x value, the slope should be the same all the way up and down. A of our options left, what do we have left? A,
We have A, F, and G.
oh yeah, we did B. So A, F, and G. So of our options left, A is the only one
That makes sense.
that makes sense for this one.
So we have F and G left. We have a sine and cosine function.
So once we get down to something like this, our best strategy is just going to be to pick a point or a couple of points and see what makes sense. All right? So scroll down here, get a better picture of both of those, I guess.
F has something that's near zero. G has nothing that's zero.
Okay, that might be a good place to start. So F,
Why are you looking at G instead of F?
well, I already looked at that. You said it's 0, 0?
Yeah. And
So when you plug in a point, do you plug it in the mat or do you plug it into the anti-gravity?
We would just
Unless
plug it
you have a
into this
horizontal line.
and
Yeah.
and think about what the slope would be. Right? So if we,
It would have a horizontal line. It'd be there.
what was the other one? Sine of y plus x. All right.
So we plug in 0, 0 here. The sine of 0.
Wait, so then why do we take the anti-derivative? We're just
I
plugging
didn't. So I didn't have to keep scrolling up and down. I just rewrote number 3 down. You think which one? 8 is F. Why?
Because if you plug in 0, cosine 0 is 1, and it doesn't have a slope on that one, and on the other one there's nothing. Or it's horizontal.
Yeah. So here, I mean, it looks like we've got a slope of maybe 1, and here you can't really see, but it looks like if these slopes to either side are really shallow negative and really shallow positive, then this one could be a slope of 0 right here. So if we think about plugging in that value, 0, 0, cosine of 0 is 1, sine of 0 is 0 plus 0 would be 0. Right? So it seems to make sense that this would be F, and then number 3 would be G. Okay, so there's a few strategies we can use here. All right, one, any domain or range restrictions. Right, that's an obvious giveaway, and that's an easy one to look at. Another is if our derivative or differentiable function is just in terms of a single variable, either just x or just y. And then another strategy is just to pick some points, plug them in, see what the slope should be. Okay? We feel okay with this stuff so far? Right, not too bad. Right? I guess that's pretty much it. Other than, on the last page at the bottom, there is a box to jot some of those ideas down in. And so, if you didn't jot any of those methods down already, okay, we can jot these down here. Right? Strategies to look for when matching slope fields. Yeah, we said any domain or range restrictions. Yeah, so we talked about thinking about parent functions, what the actual antiderivative would look like.
It's in one variable.
Yeah, if we have dy dx is in terms of a single variable, right, so that means that if it's just in terms of x, if I look at an x value, the slope would be the same all the way up and down. If it's just in terms of y, if I look horizontally, all the slopes would be the same at a single y value. And then, finally, just plug in some points. Okay, and you don't have to do these in any order. If you just want to go straight to plugging in points to determine a slope field, that's fine. You can just start plugging in points and see what matches up.
Now, are these usually calculator problems, non-calculator problems?
These are usually non-calculator problems. All right. So, any questions?